Hello everyone! In this video I will remake the presentation of my master's dissertation carried out in November 2017. The dissertation involved the design and development of an hexapod robot. This is a robot with 6 limbs. As a lot of time has passed, it is normal some things are outdated, but I think the overall information may be useful for those interested in this subject. The structure of the presentation will generally follow the form of the dissertation document. This corresponds to 6 chapters in which the main stages of this project will be addressed, and that will be presented in the next slide. This theme was chosen because robotics is playing an increasingly important role in modern societies. The design of a robot is a mechatronic challenge since it needs different areas, and because I wanted to create a free model of a robot that will be available to all interested in this topic. The objectives of the dissertation correspond to the chapters that will be presented, namely a state-of-the-art review about hexapod robots, the design of the robot, the computational study of the chosen solution, the construction of a physical prototype, the physical characterization of the hexapod robot build, and finally to make conclusions about the work developed. The first chapter will be a brief review of the main features of an hexapod robot, followed by some real examples. The body structure of a limbed robot can be divided into main areas: the body shape and the limb shape. A robot's body is rectangular when the limbs are distributed symmetrically on both sides of the robot, or it is circular when the limbs are distributed around the robot's axis. This last configuration has the advantage of not presenting a preferential side for locomotion, allowing to change direction easily, allowing more types of gate forms. It is more fault tolerant and it is more stable. Regarding the members, they can have very different degrees of freedom, depending on aspects such as the terrain, the workspace, the load, and the intended application. A common approach is a biomimetic approach. This is looking at nature, such as mammals, arachnids, and reptiles, and to analyze the position of their joints or the way they move. In contrast, one can take a non-biomimetic approach, such as limbs with wheels at the end, or telescopic limbs, examples not presented in nature. Then there are different orientations for the leg and different joints configurations. Regarding the stability of these robots, it is considered that they are statically stable, that is, ignoring dynamic effects, when the center of mass projection is within the region defined by the convex polygon formed by the support points. The smallest distance to the border of the referred regions corresponds to the value of the referred margin. This margin was later reformulated to consider the smallest distance, but in the direction of the robot's movement. However, for sloping terrain, the energy stability margin is more suitable as it takes into account the lower potential impact energy that is required to knock the robot down. For the quadruped robot shown, it is possible to verify that it is easier to make it rotate downwards than upwards, as the center of mass needs to overcome a smaller height. So, a posture that cancels delta H will be the most stable posture. This also applies to other types of robots. Regarding the characterization of locomotion, a locomotion pattern is said to be periodic when the robot's feet are raised and placed on the ground in a repetitive manner, being the form with the least associated computational processing power. A locomotion pattern is said to be non-periodic when the robot's feet are placed in pre-selected location, and as such it is a pattern that requires more computational power, being indicated for irregular terrains. For the present work, only the periodic locomotion pattern will be implemented. Within periodic locomotion, a robot can present different types of gaits classified according to the number of members supporting the robot at any given moment, such as 3 legs supporting the robot and 3 not, 4 legs supporting the robot and 2 not, and finally 5 supporting the robot and 1 not. And according to the form of movement of the limbs, as you can see in the image presented, in which if the movement is perpendicular to the limbs, we have an insect wave gait that is common in rectangular hexapods. If the limbs move only in a plane parallel to the direction of locomotion, we have the mammal kick gait, common in rectangular quadrupedal robots. And finally, the combination of the two, a mix, common in omnidirectional circular hexapod robots, and that was the gait chosen for this robot. These two criteria can be combined to obtain, for example, a 3+3 mix gait. Now I will present some existing solutions. It is possible to find more in the dissertation. The first example is NASA Athlete Robot. When the terrain is regular, wheeled locomotion is activated. When the terrain is irregular, locomotion is carried out by the members. Initially designed as an hexapod but later split into 2 tripods units that can be joined together and carry an habitat, for example. In addition to allowing locomotion, each member can interact with the environment by moving objects or performing specific tasks. The energy comes from batteries. This robot was developed to assist the return of humans to the moon. The Mantis robot from Micromagic Systems has hydraulic actuation in the form of cylinders directly connected between the different links. The system's power comes from a diesel internal combustion engine. Its main application is commercial. The objective of the Wlaking forest machine, which was designed for the timber industry, was to have high stability and a reduced impact on the ground, in order to access areas that are close to common vehicles. However, this concept can be applied to other areas such as mining, public infrastructure, water prospecting, industrial environments, and sensitive areas such as natural parks. Another example is the robot HECTOR from the University of Biel in Germany. It has its shape based on the stick inset shown in the upper right corner magnified 20 times. The 18 degrees of freedom are actuated by compliant actuators, and only by monitoring the torsion of the compliant element at each joint it is possible to detect collisions and act accordingly. The second chapter comprises the robot design. The following objectives were taken into account. Low cost, as the value should be bearable by any robotics enthusiast. Easy production translates into the 3D printing of mechanical parts and the production of the electronic board that connects the others without resorting to specific machines. And easy assembly using common materials. With regard to locomotion, as the budget is reduced, the robot must move in a plane free of obstacles, performing translations and rotations. The robot must have its own power source and must be able to run for 20 minutes. Through a smartphone application, the robot must receive the commands for its control via Bluetooth and send information about the battery status. With these goals defined, the next step involved the selection of the different components of the robot and the interaction between them. The most relevant criteria for selecting the components were the price and size of the components, which resulted in an Arduino Micro as the brain of the system, the SG90 servo motor from Tower Pro as an actuator, the Mini Maestro 24 board from Pololu to distribute power and control the servos, the HC05 Bluetooth model that works as a wireless serial port, a lithium polymer battery with high discharge rate, a step-down converter to supply a constant voltage to the servo motors, and a PCB design to interconnect the different components. To find the battery capacity in order to meet the autonomy objective, preliminary calculations were carried out to estimate the consumption of the servo motors. This image shows how the components are interconnected. The next step was to design the body structure. The shape chosen for the robot's body was circular due to its omnidirectionality, having more types of gaits and greater stability. As locomotion is planar, 3 degrees of freedom per limb are sufficient. This criteria led to the design of 7 parts: base, thigh, which has 2 motors, femur with 1 motor, tibia, electronic containers, and connection. The different parts have holes for the cables to pass through. The white fitting of the servo motor is glued on one side of the joint and the connection part on the other to provide more stability. The robot's foot is rounded in order to accommodate a rubber that cushions contact with the ground and increases friction with it. Using Inventor, it is possible to obtain the rotation limits of each joint, which will be validated in the next chapter. The third chapter comprises the computational simulation of the design robot. The program used to simulate multi-body dynamic systems was the MATLAB Mubodina program developed by Professor Paulo Flores. This program uses the Newton-Euler formulation, that is, Newton's first law is used to describe translations and Euler's equation of rotation is used for rotations. The reaction at the different joints are obtained using the Lagrange multiplier technique. For the present case, a new type of force had to be created in order to represent the contact between the ground and each foot of the robot. For this, the floor was represented by a plane and the robot's foot by a sphere. These two bodies had to be defined geometrically and in terms of their mechanical properties. Then, for each instant of the analysis, it was necessary to identify either or not there was contact, what was the relative velocity between the bodies at the instant of first contact and throughout it, and the penetration between the bodies. These parameters are essential to obtain the forces generated in contact. There are different approaches and models for calculating normal forces. The literature shows that different models can be used, so for coefficients of restitution higher than 0.7, the model proposed by Lankarani and Nikravech was chosen, and for coefficients of restitution lower than that value, the model proposed by Ziyang and Kishao was used. The forces generated in contact can be normal or frictional. As for normal forces, for frictional forces different models also exist. 2 models more suitable for computer simulations were chosen. The linear model that considers the transition between the stationary and moving state, and the hyperbolic tangent approximation that disregard that transition. Having defined the geometries of the colliding bodies, the parameters of that contact, and the models to represent the generated forces, it was then possible to correctly simulate the interaction between the robot's feet and the ground. In the animations presented, we see a sphere bouncing against the ground plane. In the first image with a coefficient of restitution of 1, without loss of energy, the sphere will bounce continuously. And in the second with a coefficient of restitution of 0.5 with loss of energy, thus obtaining smaller heights each time. In the image on the side, both with coefficient of restitution of 0.5, we see that the plane is inclined. In the image on the left, there is no friction, and as such the sphere just bounces less and less, while in the second one, with friction, the ball bounces and the friction forces it to rotate. To define the position and the orientation of the different parts of the robot, each part received a reference. With inverse kinematics, the angles of the robot's 18 joints are obtained from the positions of the robot's feet and the position and orientation of its center. This was done using vectors and the law of cosines. Direct kinematics allows obtaining the global positions of the different references of each body from the position and orientation of its center and the 18 angles of the joints. For this, homogeneous transformation matrices were used. Finally, as in Mubodina, the position of each body is described through its center of mass and orientation in Euler parameters, a function was created that used both kinematics to obtain the center of mass in global coordinates and to transform the director cosines from the transformation matrix to Euler parameters. It was necessary to obtain the angles of the joints that would allow the robot to move. For the present study, a cycloid function was used for the robot's feet, since this causes a zero vertical and horizontal velocity with the ground, minimizing the interaction forces. The basic equations of the cycloid functions were modified in order to include all the necessary parameters for locomotion. With this, different gaits were obtained for translation and rotation, as you can see in the animations below, such as rotation and translation 3 plus 3, and translation 4 plus 2 and 5 plus 1. In Mubodina, the existing actuated rotation joint was modified so that it could carry out the desired movements. This rotation joint needs to receive as parameters the desired angle, speed and acceleration for each type of movement. From the temporal evolution of the angle of the joint, for each moment of the simulation 5 points are extracted. In these 5 points, a fourth-order polynomial approximation is performed, which is easily derivable function, and then from the approximation the referred parameters are obtained. To calculate the violation of the angular constraint of the joint, relations between vectors fixed to each body were used. Once the robot was defined in the program, simulations were carried out for the mixed type gate shown in the upper right corner, which is a gate with all the legs pointing out from the robot and a predefined initial posture. This resulted in the presented animation corresponding to 5 plus 1, 4 plus 2, 3 plus 3 translation movements, and 3 plus 3 rotating movement, and also lifting and landing the robot on the ground. Using the 3 plus 3 translation as an example, it was verified that at the moment of transition between the two groups of legs, peaks in the torque of the motor were originated. After conducting different simulations with different locomotion parameters, it was concluded that as the robot's feet are round, the contact point with the ground is different from the calculated one, which makes the robot's weight distribution not uniform by the different supporting legs. By reducing the radius of the feet, a more uniform torque distribution is obtained. In terms of simulation, this makes sense since the built robot has no compliant elements, and it is therefore a rigid structure. In reality, this is not true, since as the joints will have gaps and the servo motors will not respond immediately, the stiffness of each leg will be lower than the simulated one, which will allow a better distribution of the robot's weight by the support legs. For this reason, torque peaks were not considered in this phase. From the simulations, the maximum torques of the different servo motors were obtained. The maximum torque was for a 5+1 gate, which is very close to the limit value of the servo motors. However, this value could eventually be reduced if a longer period was considered for the translation, which would lead to slower movements and lower torques, or if one chose to increase the supply voltage of the servo motors, increasing their torque. One could also choose to disregard this gate, since for the 3+3 gate type the maximum torque found is 24% lower than the limit, allowing locomotion. Another approach would be to redesign the robot structure. It was decided to proceed with the design model. This fourth chapter deals with the physical construction of the robot. The 3D printer used was the first from the Portuguese company Be Very Creative. A complete leg to test the fit of the different components was first printed. Before assembling the servo motors, it was necessary to define in which positions they should be assembled in order to maximize the angular movement of the joints. After, it was necessary to calibrate them. This means placing them in their neutral position with the right fitting, that is, the position that allows them to rotate the maximum amount both to the left and to the right. Then, for at least two predefined angles, register the pulses necessary to achieve those angles. With these values, it is possible to define a parameter I call W, which relates the intended angle for the joint with the width of the pulse that must be sent to each servo motor. Combining the physical limits of each joint with the rotation limits of the servo motors, the functional limits of each joint were obtained, which were not exceeded for the simulated gates. During the assembly of the structure, mechanical defects and opportunities for improvement were found, such as the fact that the femur, when rotating, hit the ground, and when tightening some fastening screws of the servo motors, the structure gave away, both without functional implications. Some servo motors were taller than others, with some being tighter on the femur and tibia. As improvements, it is possible to place additional openings for the passage of cables from the servo motors and rotate the servo motors so that the cables point directly to the center of the robot. The interface electronic board was produced and all the connections made, with special attention to the arrangement of the different components in the center of the robot, given the reduced space available. For this purpose, some components were surrounded by paper. In the developed Arduino program, the communication libraries with the Maestro board and Bluetooth module are included, as well as the definitions of the physical parameters of the robot and the procedures of the direct and inverse kinematics. Whenever there is no Bluetooth connection, the robot is in a low energy consumption position, with the signaling LED flashing quickly. When there is a Bluetooth connection, the robot gets up and executes the commands that are received through the Bluetooth module. Every 5 seconds, the voltage of the battery and servo motors are read and sent to the Android application, and the LED changes state. The application development was carried out on the free online platform MIT App Inventor 2. The application allows you to search for available Bluetooth devices and connect it to the robot. Select the type of movement for translation and rotation, land and lift the robot, send special commands, and display the voltage read from the battery and servo motors. In this last chapter, a characterization of the robot was carried out in terms of consumed power, mobility, and a thermal analysis. Energy consumption tests were carried out for all studied gaits, either with the robot moving on the ground or freely in the air. This allowed demonstrating that even without load, the servo motors consume a higher power than previously calculated and, despite the chosen DC-DC converter allowing the robot to function, the average current supplied exceeds the specified value of fit, as well as there are considerable current peaks, and as such a new converter was proposed. Also, for the robot's autonomy, given the higher power consumption, a new battery was also proposed in order to fulfill the intended 20 minutes of autonomy. Mobility tests were performed for both translation and rotation, with significant deviations being obtained, especially in translation, with experimental values corresponding to half of those programmed. In order to verify if the deviations were due to defect in the mechanical structure or to the type of control, a new type of gate was developed based on posture-to-posture locomotion, obtaining values close to those programmed, which indicates that the control of the robot can be improved. It is also noteworthy that despite the calibration of the servo motors previously carried out, there are deviations in the positions of the legs. For robots that do not have specific device to measure the torque of the joints and the current consumed by the servo motors, a good way to infer about these variables is through the thermal analysis of the components. This was done for the robot in a standing posture, pictures on the left, and moving in a 3+3 gate, pictures on the right. When the robot is standing up, it appears that, as expected, it is the R2 joints that eat up the most, as you can see in photo B and E, since they are the joints that have to continuously apply the highest torque to support the robot. Analyzing photo E, it is also highlighted that two of the R3 joints eat up more than the others, indicating a less advantaged posture of these legs. Regarding the electronics, thermal heating is to be expected, with the converter and the Arduino being the components that eat up the most, as you can see in photo H. Now, analyzing the robot in 3+3 gate, it turns out that it is not the servo motors of the R2 joints that eat up the most, but 4 servo motors of the R3 joints, as you can see in photo B. This may be due to the fact that these legs are repeatedly in more unfavorable postures, having to apply higher torques. With regards to electronic components, heating is greater as the power consumed is also greater. It should also be highlighted that the power cables also heat up given the high currents being consumed, and it is recommended that both the side component and the electronic containers have openings to allow better dissipation of the heat produced. In conclusion, it has been demonstrated that robots with limbs have tremendous potential given that the wide range of available configurations allow them to perform a wide variety of functions depending on the intended application. It was found that due to the fact the simulated robot did not contemplate the round fit and the rigidity of the structure correctly, the computational results exhibit phenomena that physically do not seem to have been verified. As with any prototype, aspects to be corrected were identified, namely a converter capable of supplying more current and a battery with greater capacity, with alternatives being proposed, as well as aspects of the mechanical structure to be corrected. It is demonstrated that it is possible to obtain a functional robot for approximately 167 euros. In terms of future work, in order to bring the simulated model closer to the built one, the inverse kinematics can be reformulated for the reason expressed above. Compliant elements can be added to the simulated model, as well as indices created to evaluate the stability of the robot. The electronics and control can be improved. For example, the new member of the Raspberry Pi family that already has Bluetooth and Wi-Fi internally has greater computational power and can directly control the servo motors. As far as the mechanical structure is concerned, there are defects and opportunities for improvement, as well as, if the budget allows it, more powerful servo motors with the same size are available. allowing the application of new types of gates. Finally, it is recommended to purchase servo motors directly from the original supplier in order to eliminate quality defects. If you have resisted up to this point, thank you for your attention. For more information, check the links in the description. If you liked this video, hit the like button and subscribe for more.